Good afternoon, friends. It's great pleasure being able to give an opportunity to present, and it's been a long day, very interesting one, and I think the lunch was also good, so we can expect some, but we'll try to make it, interesting. Today's topic, we want to cover serverless data processing on Knative, which is a Kubernetes-based serverless platform. We want to cover this whole presentation in 3 parts. Part 1, we're going to build on what is Knative, the key capabilities, concepts, and the component of Knative. So that will set up the baseline understanding for understanding the next part of the talk, which is about how to employ Knative to solve for couple of data processing use case we have in Appdirect. And in the third and the concluding segment, we want to give a ringside view of how does this technology Knative fits in the overall data processing serverless ecosystem. It's fairly new, so we want to present our learnings and point of view. So that's how we will go through this presentation. So let's get started. So can I have a quick poll, like how many of you have adopted or are aware of Kubernetes as a platform? Can I have a show of hands? Okay, good. How many of you have adopted any serverless frameworks or platform like AWS Lambda or Cloud Functions? Cool, thanks. Okay. So what is Knative? Knative is a Kubernetes-based modern serverless platform to easily build, deploy, and manage serverless workload. But like the question is, what is Kubernetes in first place? It's a container orchestration platform. Like we know about Docker containers, RKT containers. So it's a platform which is used to manage containers in a big deployment environment. It came out of Google. And Knative is also, it was launched in year 2018, last year, June, by a consortium of Google, Red Hat, Pivotal, IBM, and a lot more other players. But primarily, it has come out of Google's experience in building serverless system inside the data center. So the same way Kubernetes came out of Google, so they are trying to build out open source stack using the principle and the practice they already had in Google for big load processing. If you look at serverless and serverless functions as a broader term, what does it mean? Actually, there are so many definitions, so it's very difficult to associate one thing, but there are certain underlying key properties such system exhibit. One of the key properties is that your compute model, the compute model could be one container, like if your container is your unit of compute, the compute model is driven by request. Only if you have request, you want the container to be running. If there is no load, you don't want the container to be executing and consuming resource. So that's one of the key underlying properties of a serverless system is. Secondly, it's primarily the systems are event driven. You want to execute some compute when the event occurs. The event could be an API call. The event could be actually the records of a file, log file, which have been parsed into individual records. That can also be event. So how you define event is based on your use case. Generally, such computes are stateless. So in the morning, Vinod talked about a key shift which is happening, that separation of compute from data. He said compute is stateless, data is stateful. That's always how it's going to be. So these functions are always stateless. They get one event, they have to process one event, and they don't remember anything beyond one event. And we talked about the request-based model, that the compute runtimes come up and go down. They are ephemeral, they are not always running. And why serverless? Can we have a system without servers? Definitely no. There are servers always. The question is, as application developer or as operations, are you exposed to those servers? Are you responsible for spinning them, monitoring them, managing them? The key concept in serverless, somebody else is doing that for you, but there are servers, and you don't pay for those servers if you're not using those servers. So those are the key properties of serverless. If you look at the drivers for this serverless ecosystem, why so much hype and why so much excitement? The key drivers are, we want to have higher developer velocity. We don't want developers to spend time doing operational tasks. They should be doing their core functional or use case based development. We want lower operational overheads because operation is something which is an enabler, not the money generator. And last but not the least, we talked about pay-per-use, request-based compute. So what it means, if your compute is not running, you're not consuming resource, you're not paying for the money. So being able to save cost is one of the key drivers from business perspective. So this is what is driving the interest in serverless. Okay, now coming to Knative as a serverless platform. So what are the key building blocks of Knative? So Knative is consisting of 3 key components. The first is called build, the second is called serving, and the third is eventing. So what is native in Knative? Why it is native? Knative basically extends Kubernetes through the standard mechanism of custom resource definition. So anybody who has used Kubernetes would be aware of CRDs. So these are extension points built in Kubernetes to add additional capabilities to Kubernetes, which fits natively into Kubernetes. Like the kubectl tool you use will also be useful to manipulate custom resources. So Knative leverages CRDs, the controller and dispatcher pattern of Kubernetes. So it's built natively using the same Kubernetes architecture, which Kubernetes itself is based on. And secondly, it leverages the components of deployment, pods, and autoscaler of Kubernetes. So that's the native part of Knative. So let's go into the individual components one by one at brief. So the build component, the capability which the build component gives is that you have a code in GitHub. The moment you merge a PR on the main branch, you want a container to be created. So that's the capability build provides. It gives you a way to specify your entire build process as a set of steps. Then you have builders, which are actually containers, which will execute those steps. And then you have build templates, which tell you whether it's a Gradle build or Maven build or Java build. So why they want to build this component in a serverless system? Because you talk about serverless velocity. What if developer have to spend half a day getting a container from the code? That's no velocity. So the moment you check in, you'll get container without running any Jenkins or any CI/CD server yourself. The containers will run inside your Kubernetes cluster. So you are actually serverless even from a build perspective. So that's the capability of the build module. Coming to the second component, serving. So we talked about request-based compute model. Only when a request comes, you want to run the code and not occupy any resource. So the way Knative provides this capability is through the concept of revisions. So if you look at the diagram, let's focus on the bottom part. A revision is nothing but a snapshot in time which contains your code and the configuration. So if you look at 12-factor app, we talked about separation of code and the configuration. So at a particular point in time, a combination of code and configuration is your revision. As you fix bugs or do more releases, you're creating more revisions. So we have a number of revisions. The configuration basically keeps track of the number of revisions you have created over a period of time. Now, you have a revision which is code, running code. You want to expose that and make it available for consumers. So that's what a route does. So route provides an addressable endpoint for your revision, so that it's available over some protocol, typically HTTP or gRPC. So routes basically provides a network ingress into your revision. And then to tie up everything, we have a concept of functions. So this is how conceptually it is implemented. These are all CRDs in Kubernetes. But coming more concretely in terms of as a developer, what do you see as a functions? So if you are used to Kubernetes, you basically deploy a container inside a pod. So functions which you write are deployed as pods. So they are not different than any microservice you would develop on Kubernetes. They are still pods. The functions you write are HTTP addressable endpoint. They're exposed via the gateway. So your function is nothing but a HTTP endpoint. So no change in core concept on the side of consumer. They still are talking to some HTTP endpoint. Now the most important part is like the pods can scale down to 0 when there is no pending request. So this is that beauty of not having any resources consumed when there's no request. Suppose your workload is such that only once in an hour you run some job and then there's nothing, or it's very sporadic. The load is very sporadic. You don't want to have 5 pods running and consuming 5 resources. So only when the first request comes, then the pod will be activated. Otherwise, we'll see this in action when Arvind and Priyank talk about it. Otherwise, there are no pods running. That means no cost. And then one of the challenges which backend developers face is to scale the system, horizontal scalability. So we spend a lot of energy trying to build scalable architectures. Auto scaling is provided out of the box here. As a end developer, you have to just do very basic configuration, and we'll look into what the configuration. You get auto scaling pretty much cheap and out of the box. And then when we release the software, we want to do canary testing. We don't want to route the 100% traffic to the new software. You want to do 50-50 split. So all that is possible through routes and canary deployment. So these are the core capabilities in serving, which helps in faster development and faster deployment. So we talked about functions, but how does a function look like? If you are a Java programmer, this is anatomy of a function. So you have an entry point main. Any Java program will have main. You just have one REST controller with a post endpoint. It takes a request, it gives a response. This is all a function is. If you look at what we have imported, there is nothing Knative specific. It is pure Java Spring Boot. It could be a Python code. It could be a Node.js code. It could be Go code. There is no binding to Knative anywhere. It is a simple hello world HTTP endpoint. And that's what, as a developer, you'll write. This is all you have to write. Just that your business logic is the only thing you'll focus on. So this is code, but how do we deploy this and convert that into a function in Knative? So this is a configuration for your function. We call it like manifest in Kubernetes. So the key thing you look at in the bottom is, once the code is built into a container using the build component, you would have a Docker container in some registry. So if you look at the spec container image, it's a Docker container. We talked about auto scaling. Okay, so as a developer, if you look at the auto scaling set of properties, you can actually configure it on a per function basis. So the way auto scaling algorithm works, one of the auto scaling algorithm works in Knative is, it's called concurrency based auto scaling, where the key concept is, as a developer, you can define a target. If you look at the target value 10, what it means is how many in-flight requests per pod you want to maintain. It's 10, like, so if there are 10 in-flight, my pod can actually is able to handle 10. If it grows beyond 10, I want a new pod to be spun up, otherwise my latency is going to go down. So you decide what's the right value for you, 10. So that's a hint to the concurrency autoscaler. And then you define the limits, like minimum scale and max scale. So minimum means how many pods I want it to be running all the time. Actually, you can give it 0. So it will be not running when there's no request. But sometimes because of the cold start latency, you want one pod to always be there. Because when the first request comes, there's a cold start and there is some latency. You want to avoid that because of your use case. So you may want to keep it 1. Nothing which says it has to be 1. It can be 0. And ideally, it should be 0 for a serverless platform. And the max is 100. So autoscaler is not going to go unbounded because you still have to manage some cost at some point. So you bound it between 1 to 100. And whenever you have more volume, it will start spinning a pod, and that you will see it in action. So this is all the configurations. So as a developer, this is the only thing you have to be aware of Knative. Everything else is standard Kubernetes. You are not exposed to any platform or any operational concerns. So we covered build, we covered serving. Now we talked about being event driven. So you have functions. Somebody has to trigger the function. Okay, it could be as simple as somebody making a API call on your endpoint. If you are writing some standard REST or SOAP APIs. But in context of data processing, near real-time data processing systems, it's mostly event-driven. So you have events which are coming from different sources. It could be a file source, it could be a live source like Twitter, or it could be even from Kafka. So eventing is a core component in Knative. So if you look at this conceptual diagram, we have sources and we have service. So we covered service in the previous slide. A source is nothing but a producer of data. So there are out-of-the-box available source. You can write your own source. So it can connect to any system, scrape data, and emit events. So that's what the role of source is. Now sources, they typically can directly bind to a service, but that's not what you want to typically do. It's a strong binding. You typically, a source will be configured to emit data on a channel. Channel is an abstract concept. It will be backed by a real messaging system like Kafka, GCP, PubSub, NATS. Or you can, if you want to have RabbitMQ, you can develop RabbitMQ. So channel is nothing but a mechanism to discover and distribute events. And services are the end consumers of event services. But the way they express their interest in the event is by creating subscriptions on particular channel. So you create a subscription which is like, okay, as a consumer, this is channel I'm interested in. So that's what the whole eventing system is all about. We'll see how we have used this in a real life use case for data processing. So as I said, it's an ecosystem, and you have support for a lot of channel out of the box. There's in-memory channel which is not meant for production, just for test capabilities. You have a channel which is backed by GCP, PubSub, Kafka, NATS. So pretty much the kind of popular system you would use in a big data environment, all those are are available as channels. In terms of sources, you have GCP PubSub source, AWS SQS source. So any message or event in those messaging system will emit an event into channel, and you can invoke a function based on an event or a message in Kafka. And as I said, this is extensible model. If there is source which you care about is not there, you can write it up. So the sources are pretty much growing over the period of time, but it's an open extensible ecosystem. Okay, so that was all about Knative. Now shifting gears a little bit. So we are from a company called Appdirect. We are into the multi-sided digital commerce platform, where we connect providers of products or services. We connect resellers, the end consumers, and a platform partner. So we work at the intersection of a lot of different entities. And if you look at the diagram, we have shown like we do sell SaaS software like Microsoft Online, G Suite through a platform. And some of the use cases we're going to demo are from this domain. The question is like why we are interested in serverless as a org. There are business drivers. Many of our workloads are very seasonal or variable, so you don't need to have containers running all the time. We do have a multi-cloud strategy, like we want to be available on GCP, we want to be available even on-prem, Kubernetes, because some of our partners, they don't want to be on cloud right now. We do have an investment in Kubernetes, we want to leverage that. We want to reduce our we want to increase our developer and operational velocity and manage costs. So key drivers, most of the orgs will have similar business drivers. But from an architectural point of view, why we're interested is because we want to evolve our microservice to serverless functions. So we want to have evolutionary path, as well as we have a lot of events in our domain, which are published on RabbitMQ today. So we want to publish them onto channels in Knative so that we can have functions based on them. So that's our motivation. And now we'll shift gears. I'll invite Priyank to talk to a particular use case in data processing inside Appdirect using Knative.
So, hi, I'm Priyank, and I'll walk through the first demonstration. So the first use case we have at Appdirect is processing, near real-time processing of files. So these are log files in a way. What happens is, as Tarun has discussed our business use case, there are software providers on our platform who want to collect and report their usage that is happening on their softwares, and they want to be able to bill their clients. So that information passes through our system. We basically collect that information, we rate the individual usages, and we produce the billing and invoicing for them. So for example, one of the use cases might be in a telecom domain, you have call data records. So every time you make a call, use your internet plan, there's a usage that you incur. So each of those records are sent to us in the form of files, or maybe even API calls, and we kind of rate it near real time, and we add it to your billing and invoicing systems. So I'll walk through the components. So this diagram that you're seeing, it's partially a reflection of what we do, and partially it's a contrived example to just drive the point. So the files that we receive come from varied sources. They may be GCP storage, it may be AWS S3, remote file server, or even API calls. So only thing that in our system that is tied up to the source is there's just one service, which is kind of an adapter to connect to these varied services. So it might be, for example, you see GCP source, AWS source, or remote file system source. Then we have Parser and Resolver. These are basically parts of the pipeline. The role of the parser is so once you get a file, the source basically splits it into records. These are just strings that are passed onto the stream to the next stage. So the parser then takes each record, it tokenizes it into key value pairs, and this is all done based on a user-defined configuration. It's a kind of a schema that is configured into our system for each kind of file that we want to process. And once it's configured, we can continue parsing the files easily. So once we tokenize, we pass it on to the next system. The resolver is responsible for, as the name suggests, resolution. The resolution basically means applying some data manipulation, business validations, rules, and so now we have some raw data, but we want to be able to map it to meaningful data on our system. We have entities, we have some domain entities in our system that we want to map it to. So Resolver does that. Again, this is driven by the user configurations. And what we mean by domain is, for example, in billing, we'll need to know for each event that we receive. For example, who was the user? What product were they using? What was the quantity that they used? And things like that. At a minimum, we'll need this information. So Resolver does that of mapping it. It's again configuration driven. There's no code that has to be written for each new type of file that we receive. So one thing that I'm skipping right now is the channels. Channels are just transportation medium for sending the data to next stage. We'll come back to that, but yeah, that's the role of each component. So if we see, as Tarun has already talked about the build portion, we are using Knative build component to build our services. Basically, we just give it the source code, and it generates the container, sends it to the container registry, and it's available to be deployed on Knative. So now, if we look into each component, we can classify it into 3 parts. The first is channel. Channel is your medium to send data across the pipeline. Second is the source. Source is a special type of service, which is in the world of Knative, it's not exactly something that you want to scale. It's a service that keeps on running. And the other 2 services, Parser and Resolver, and even some of the other downstream systems that we are not considering right now, are the things that we want to scale up or down as they are needed. So these other services, for example, the Parser and Resolver functions are basically just subscriptions in terms of Knative. So I'll walk through each one of them. So first we can see channel. Channel is just a way to be able to communicate data between different components. So it falls under the Knative eventing part. What it provides you is the buffering of the events, persistent layer for the events, and sending it across to the right subscriber. It's the responsibility of channel to send it to the subscriber. Even if the subscriber is down at a given point, it has to take care that it is somehow sent to the subscriber when it comes up. So what channel provides you is an abstraction between your code and the underlying messaging infrastructure. You are not tied to a messaging layer. For example, you don't have to depend upon RabbitMQ or Kafka or NATS, for example. You just have to worry about how to get that information from the channel, and the underlying messaging infrastructure does not really bother your code. So different providers, for example, Kafka and Google PubSub, have their own backing implementations of these channels, and they can be plugged in and out as required. For our demo, we are using an in-memory channel, which is like an experimental thing. You cannot take it to production, but you can use it in development. The next component is the source. So now the source, as I said, are adapters that pull data or get data from different sources. These are the systems that we want to keep running every time as long as they are required. Now we have written this code, but how do we deploy it into Knative? If you don't want to scale it, these are not really functions that we want to scale up or down. We want them to be kept on running. Now here is where eventing sources come into picture. Eventing sources are basically, it's an abstraction which basically says that you have a source, you have a piece of code or a container that has to be kept on running on a single pod has to be running all the time, and it needs to have a sink. So sink is basically, it says that as a source you are generating some events. You want to be able to send it to an endpoint. So sink is something that tells you where the events have to go. Now the source generates the events. What I mean by that is, in our example, it pulls a file, it splits it into the records, and it sends to the next channel. So now for this, we have used a concept called the container source, which, as the name suggests, is a source which takes container as its input. So the container source is just any Java, any kind of a code that you write, and you can just define it or configure it as a container source, provide it a sink, and it will work out of the box. The third component that we are looking at is the parser and resolver. These are functions. These are what we understand by serverless entities, the lambdas that we talk about. But in case of Knative, we are not exactly tied to any function implementation. It does not have to be a cloud function or a AWS Lambda. It's just a piece of code that you write for your your regular, developing your regular code. So, for example, resolver and parsers are simple functions. They take an input event, they emit an output event after applying some manipulation. So, when you write the code, you're writing a function, and you are just providing a single endpoint. That endpoint is HTTP addressable, so that other systems in the Knative can communicate to it. So that's all you have to do. It's like an API call. Now these are services. So when I talk about these functions, these are simple services in Knative. How do they are not aware, or they do not care about where the events are coming from. So you can call an API and invoke this function, or you can send it and send an event through the channel and invoke the function. It behaves the same way. So how do you fill that gap? So subscription is a concept which basically ties up your service and the channel. Subscription tells you, okay, now there's an input channel where you'll be receiving your events, and there's an output channel where you have to send your events, which is optional. In case of parser, we are reading from records, we are sending it to a parse channel. So that's all there is to this part. So as I said, we have written the code. It's all about configuration as to where it fits into the Knative model. So for example, when we talk about the source, we say that it's a container source. We tell it that there's a sink, which is a channel, and the name of the channel that you have to send the records to is records. Then a subscription. For example, if we look into the subscription of a parser, we first define it as a service. We link it to an image where it has to pull the actual code from. We give it some auto-scaling factor. And then we basically define a subscription. So subscription is what ties up your channel and your service. So you're telling it the input channel, you're giving it an output channel, and that's all. So we'll try to run an example, basically just to see. So if the internet permits, we'll be able to upload this file to the storage, and it will trigger a chain of trigger the other functions. So if you see we missed the parser part, but resolvers. As we are receiving thousands of events at a time, the resolver keeps on scaling. So there are n number of pods that are running to service the events that were generated. Since I pushed a file with 1,000 records, the resolvers are just as per the need, they're growing. So I'll try and see if we can see it on the metrics. So this is a message dumper, which is nothing but the end. Once it's resolved, we are just dumping it into a log file. So I think it's not getting, the metrics are not getting updated here. Yeah, it's coming up. So as you see, up until this point, there were no pods that were there. This is just a graph of the pods that grew. So there were no pods because there was no consumption. As the requests came in, there was a demand for some number of pods. So based on how many nodes are available, how much stress there is on the system, it was able to provision some 10 pods that serviced, that ran the service and consumed the events that were published. And if you see into this here, all the pods have done their job. Now they are terminating because they don't have any work to do. Yeah. So that was the first demo. I'll invite Arvind to continue and build on what we have already talked about.
Thanks, Priyank. I'm Arvind. I'm currently working in capacity of a software developer at Appdirect. So there is another use case, another interesting use case that we would like to bring out to your notice. So basically, we have a middleware microservice which kind of acts like an aggregator of events. So basically, you have your ISVs, be it Google, GitHub, Facebook. The point being, they send events to this microservice, and this microservice acts as an aggregator of those events. It manipulates those events, enhances those events, transforms those events, and then forwards it to a sync microservice. So the problem in this case is that not all ISVs are alike. So a Google might send events at a frequency which is different than a lesser known ISV. So that poses a potential problem to us. So how do we handle this? We can't have a microservice which has like 10 instances ready at all time, because that would be an overkill in cases where the data is not, or the events are not coming. So in that case, in order to solve this problem, we leveraged upon Knato's ability of scaling down to 0 and ad hoc upon request, like serving pods upon request as and when the load comes. So we'll have a look at that. So we used two approaches in order to solve this problem. First was using writing our own custom router function, which is the block in the middle. And the second approach was an upcoming enhancement to Knative itself, which is the broker trigger mechanism. So let's start with the first one first. So anything in gray is a service that we have developed. Anything in other color is either available by Knative or is a third-party application. So basically, all the ISVs post their data to a webhook handler, which is basically a typical microservice out of the Knative infrastructure, which then pushes the data to a Google topic. We have a GCP PubSub source, which is similar to the source which Priyank mentioned in his demo. So basically what it does, it listens to a topic, it posts events to a channel. On that channel, we have placed a custom router function. Its sole responsibility is to look at that channel, infer the type of the event, and accordingly decide which channel it wants to post that event to. And then there is a sync in the end. So we'll try to run this one. I'll just get pods again. So right now there is no pod for GitHub that is running right now. So what I'll do is I'll send a Postman request to create a PR in GitHub. In this example, I am simulating the ISV because it is technically not possible to like make those API calls. So I'll just send a create PR request and let's see what happens. So as you can see, immediately once I sent a create PR request, it was able to identify that the source was GitHub, and accordingly it instantiated an instance of GitHub function pod for me. And we can basically check the logs to see if the message is actually being received. So what I'll do is I'll just pull out the logs for you. I'll increase the time frame, my bad. Yeah, so we were able to see the actual message that I had sent. It's base 64 encoded, but trust me, it's the actual message. So yeah. Okay, before moving on to the broker trigger approach that we used, what I'll do is, in order to simulate a load on the system, I'll use JMeter to simulate a load of 1,500 users, and we'll be able to see the same system at scale. Yeah, so it's actually instantiating the services that it basically needs. We'll get back to this a little later. So like I said, in order to solve the problem of routing it to multiple channels, which is natively not available in Knative, we had to write a custom router function. But an upcoming feature called broker trigger kind of like fixes this problem, wherein a broker could be considered to be an event mesh. So what that means is that it's a mesh on which you can keep on sending your events. A trigger is basically subscribed to a broker, and based on some filter criteria, it would decide which trigger to invoke. We'll have a look at the actual semantics and actual structure of each of this a little later. But in order to make this work, it kind of uses another cool concept called cloud events. So CNCF has recently approved 0.2 version of cloud events. So the problem with events is that each ISV defines events in its own format. There is no consistency amongst ISVs. So in order to solve this problem, CNCF has decided to come up with a common event format, which basically, the important parts here are the event type, the source of the event, and the event ID. Your actual data comes in the payload. So let us have a look at how the broker and the broker and the trigger actually look. So broker basically is backed by a channel. This can be any channel of any type, be it GCP, Kafka, NATS, or in-memory. So in our case, we have used an in-memory channel. A trigger basically tells your broker how to send the events to a particular function. So in this case, this my service will receive events which are of type dev knative foo bar. Let's have a look at this in action. So basically, this is similar to the last demo that we did. So this time around, I'll send a PR create request, but this time this would be in the cloud event format, and this would be sent to the broker that we have created. So as you can see, invoker got triggered, which then decided upon which function it has to call. So in this case, it's decided to call the broker GitHub function. So this is that architecture. So basically, a broker via a trigger can call any of these functions. So like I said, we actually made a load test on the GitHub function. So these are the results for that. As you can see, as the number of users was increasing, it was able to scale the pods in number. So in the end, there were 7 pods that were active at that moment. And as you can see in the logs, those are no longer needed. So those are gradually terminating. Let's get back to the PPT. Okay, we have already covered this. We saw the demo. We saw a custom channel routing demo, and we already did load testing on it. So the challenges that we faced in this case. So the problem was that natively, the routing capabilities are still in a nascent state. They are not ready yet, but they are actively being worked upon. Also, eventing by itself is evolving, which means that it is prone to changes, it is prone to breaking. And more importantly, but that being said, the problem is that in a forum, we were facing a problem, and we just wrote a question in the forum, and they got back to us immediately. And within a day, we were able to get their tech lead, the Knative development tech lead, on a call within a day. So it's actively, Google is actively involved into this. It is backed by big giants. So that is why the future seems to be rosy, at least from our point of view, for Knative. Okay, so in order to continue, in closing, I'd like to call Tarun and Priyank.
So we're coming to the last section of this. So we looked at what is Knative, the kind of data processing use case we implemented on top of Knative. But the question is, this technology is very new, evolving. So how does it fit in overall data processing ecosystem, and how does it fit in the serverless ecosystem, and how you should think about it when you leave this room. So this is our point of view. Definitely we can differ on opinion, but what we would like to say is, if you are already managing Kubernetes cluster or have investment in Kubernetes expertise, then it's a good thing to start thinking about it, because your developer onboarding is very easy, your ops onboarding is very easy. But if you're already having an AWS cloud native architecture, which is strongly bound to AWS, you're already using Lambdas, S3, you may not want to think about it now, unless you have a multi-cloud problem or strategy to solve. So if you're on Lambda, pretty much Lambda gives you all this provides today, and it's more tightly integrated with the rest of the AWS ecosystem. If your strategy is being multi-cloud for business reasons, and you want to move to serverless, then this is a very promising, because the only dependency it has is on Kubernetes. Kubernetes is already available on all the public cloud platform. Kubernetes is widely supported on-prem, and it is can say one of the most de facto orchestration platform in the planet today. So this gives a very good enablement for a multi-cloud server strategy. The third reason is like your use case, if it has variable load, and you're not talking about very complex data processing DAGs. So why we are talking about why it may not be suitable is because if you look at a function, if you map it to your data processing primitive, it's like a map. It's a map function. It's not a reduce. It's stateless. It gets one request, it gives one response. So to model anything more complex than a map or a flat map is very difficult with any function. It's not about Knative, it's about a programming model. So if you have very complex DAG and use cases, you may want to continue using whatever processing framework like Spark or Flink. They have much richer programming model. They are much more scalable. Right now, I'm saying Knative will be much more scalable in future once it goes the evolution curve. Second thing which it lacks right now is the concept of a step function in AWS. Like you want to orchestrate calls between multiple functions, so that capability is not there as a programming model. But I would like to bring out one thing. What's the design philosophy behind Knative? If you talk to people in Google, if you look at what the tech leads are saying, the way Knative is designed is to be a platform for serverless. It's not going to be the framework. So they're providing basic primitives and building block, and they expect ecosystem to build abstractions and tools and frameworks. Already IBM OpenWhisk is ported on this platform. Spring Riff is ported on this platform. Red Hat has adopted this. So the objective of Knative is to act as a platform on which you will see a rich ecosystem of frameworks being created. So right now it's bare bones, and it's like you're using core operating system primitives to write higher level business logic. That's the kind of thing you would have seen today. But that's how it is intended, and it's going to be evolved. But one great point about Knative you would have seen is like if your developers are already proficient in some programming in Java, whatever it is, Python, Go, they don't need to learn anything more. They can start writing functions. There's a basic deployment concern about configuration, but beyond that, there is not much learning curve. So I think there's a case study from Deutsche Telekom. They could port an existing microservice to Knative in a matter of 1 week. And that's how easy it was. And as I said, the ecosystem is evolving very fast. Project Riff, which is on Spring, Camel has been ported to this. So yeah, we'll just pause here now. We are open for questions. Okay, so we looked at events, okay? So API is one way to expose your function. If you are creating a source and publishing your events to a channel, then your functions get triggered. But apart from HTTP API, if you want to directly invoke a function, then gRPC endpoints are going to come. But yeah, if you want to be a part of your processing DAG, it could be just a subscription on a channel, and it will get invoked. So API is not the only way to trigger a function. Not exactly. So as I said, like this is like the core primitive that you write functions, but we looked at how did we stitch up a set of functions into a linear DAG, correct? So you can build those kind of DAGs on top of it, but it is still not strictly data flow yet. Like maybe data flow in future as they evolve it, the steps in the flow could be your functions, but you need to be hosted all the time. Data flow can do, you have to use a hosted service, correct? You're talking about Google data flow or Spring data flow? Yeah, it's like a hosted data processing platform. But if you look at the intent of this, it can be used in data processing, it can be used in normal, your microservices, services-based architecture also. So it's not just tied to data use case, it's more general purpose. Okay, so we didn't go in the internals of this. So Knative right now leverages Istio as its networking layer. And there are concerns in the community about wanting to adopt Knative but not wanting to adopt Istio. So now they're decoupling the gateway part, networking layer, so that anybody can write a new CRUD, CRD, and support for Envoy-based adapter is coming. So there's an underlying service mesh which is not exposed because you are not supposed to worry about that layer because the kind of abstraction they want to build. So it has Istio in between. So Istio manages the routing. We looked into the route and the revision. So how does, it's an interesting question. How does, from zero you scale up? You get the first request, HTTP request. How does it scale up? So the request goes to an Istio virtual service, which has a route. The route goes to activator, which buffers the request. It creates the first pod. and proxies the call to the pod. So definitely a service mesh is underlying. It's not visible to you. Can you just pass on the mic, please?
My question is, how does the function reliability maintains in stateless or the serverless Kubernetes?
Take this. Sorry, we didn't. Can you just repeat the question?
I mean, the function is getting triggered, right?
Yes.
Internally. So how the function reliability maintains internally, like the function will get triggered or not, and how do we come to know if the function triggered or not, or we are getting the correct response or not?
If I got it, like how the function knows it got triggered, that's one part of the question, correct?
Yes.
So a function doesn't need to know. When it gets called, it gets the request, it's to do its job, return, and that's it. So that's from application development perspective. You don't care when it gets triggered. Once you're triggered, you execute your logic and you return the response. Now, if there are problems in the invocation, we looked into the Prometheus dashboards. So a lot of metrics is collected. In fact, we didn't show you all the dashboard. You will see failure rates also. So it's active monitoring is built into the core platform. Yeah, a very good question. So all the pitfalls of distributed computing are there at a much larger scale now because functions are coming and going. So if you look at observability, we talk about 3 parts: logs, distributed tracing, and metrics. All 3 are available to you as a tool. So based on what kind of logging you will do, it will get aggregated, and through Fluentd you will be able to see it. You have distributed tracing through Jagger, Zipkin available, and metrics are through Prometheus. So this is all coming out of the box. You can deploy any solution of your choice, and that will help you with debugging those things. So if your pods are failing, let's say your function comes up and fails because of some code reason or some environment reason, you will see metrics in Prometheus. You can set up alerts also that my failure rates are crossing more than 2%. So all those things are built into it. Plus you can configure it. So it's typical distributed systems kind of observability problems we have, and same tools are applicable here. Is the question about your infrastructure scalability? Okay. So we had set up this cluster on GKE. So at the infrastructure level, whether you're in GKE or in AKE, Amazon Kubernetes environment, if that you can configure for horizontal scalability based on triggers, then Kubernetes, which runs on top of it, can make requests for more resources based on those auto-scaling policies. So once the function starts scaling out, it makes a request to Kubernetes scheduler, I want more pods. And now Kubernetes goes to the underlying infrastructure and leverages auto-scaling to scale out your infrastructure in terms of number of VMs. So it depends on the configuration, whether you want to do that and what limits you want to put. But yeah, that is what is possible. It's like functions, they start raising demand for pods. Kubernetes starts raising demand for nodes, and AWS or GKE will start allocating more nodes, and it will shrink auto. So that's the key. Like the whole stack has to be elastic scalable, otherwise you can't get elastic scalability. So if you do on-prem, you will not get the true benefit. You may just run functions, but you will not get a true scale-out, scale-in thing. I think we can take this as the end of the session. Thank you so much for your time. Thank you so much.